All right, now we want to switch gears and look at sort of the second fundamental problem in calculus. So the first one was to find a tangent line to a curve, or to find the instantaneous rate of change, and then we saw a bunch of applications for that. The second one is to find the area under a curve. So we know how to find the area under linear regions like regular polygons or whatever. How do you find the area under a curved function, right? How do you find the area enclosed by a circle? Well, we know something about that. So the way we will do this, so we want to find the area of this shaded region here. So the area under the curve y equals f of x on the closed bounded interval from a to b. So the method that we will use is one that's pretty old, maybe ancient Greek old, but later looked at again in the 1800s by Riemann. Is this slice, approximate, refine. And so what we will do is we will take the region and break it up into a bunch of slices, right? A bunch of rectangular slices. And then, right, we'll say what we mean, what the height of each one of these things should be in a minute. And then to approximate the area, we will find the area of each rectangle and then add up all of the areas of the rectangles. And so that will give a reasonable approximation for the area. And of course, the more rectangles that you use on this interval from A, this is fixed, right? So the more rectangles that you use, the better the approximation will get. That's the refined part. In other words, we will let n be the number of rectangles, and then we will let n go to infinity. Okay, so before we can actually do one of these types of problems in full, there's a few things that we need to look at. I'm going to say what I mean by each of these things. Let's go into a little more depth for each of these parts. So the objective to find the area under the curve on a closed bounded interval. So we've got this function y equals f of x, and we are on the closed bounded interval from a to b. So we are looking at the area bounded by these lines, curves and lines. Okay, so remember, in order to do that, we said this was a three-step process: slice, approximate, refine. Let's look at, I think, probably the most involved aspect of this thing. That's the slice part. Here's what we mean by that. So I'm going to take some points in between A and B. Let me let A be x0. I'll throw in an x1 and then an x2 that's bigger than x1, an x3 and x4. In general, I will say the ith subinterval, or the ith rectangle, is here at xi minus 1 to xi. Blah, 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 right? Throw in some more points, and then finally we've got xn, which is b. So here's x0, and here's xn. So I am going to use n rectangles in order to approximate this area, and we'll have a notation for that. So the width of each one of these things, right? So the width of the first subinterval is just x1 minus x0. The width of the second subinterval is x2 minus x1. In general, the width of the ith subinterval, it's xi minus 1. Right, so delta x sub I, the change in x, is equal to this number x sub I minus this number, which is x sub I minus 1. So now we've got the width of a rectangle. And now what I'm going to do is choose any point, call it xi star, any point somewhere in this subinterval. Let's say xi star is here. So there's xi star. And I'm going to use this point to determine the height of the ith rectangle. So if you like, what's the height? I mean, what's the height of that rectangle going to be? Well, just trace xi to this point up here on the curve. And so the height of that thing is going to be f of x sub I star. So just take this thing and plug it into the function f of x. And so when I do, I just get f of x sub I star, whatever that happens to be. So now here is the height of the ith rectangle. Right, so far we've got the width, delta xi, whatever that happens to be. We've got the height. Choose some sample point in the ith subinterval, plug it into the function. That's going to be the height of this rectangle. Right, and so now what's the area going to be? Well, it's just the width, so delta x sub I times the height, f of x sub I star. So here is an expression for the area of the ith rectangle. Okay, so that's the slice part, right? It's just the height times the width. That's going to be the area of the ith rectangle. Make sure you're good on this notation. I know there's a lot of notation going on. There's going to be a little bit more, and then we'll be able to go through one of these problems. Okay, now that we see what the slice part of this method gives us, right? The slice of, right, take a slice out of this region, and that's the ith rectangle. So the area, it's the height of this ith rectangle. So remember, the height is choose some sample point in the ith subinterval and plug it into the function. That gives us the height. And then the width is just whatever xi minus x sub I minus 1 is, and we called that delta xi. So it's the width times the height. That gives us the area of the ith rectangle, or the slice part. Now to approximate, we do the same thing, right? So here's the first rectangle. So some sample point, call it x1 star in here, right? Plug that into the function. That's going to determine the height of the first rectangle. So that's the height of the first rectangle times the width of the first rectangle. So there's the area of the first rectangle. Do that again on the second subinterval. So right, here's the second rectangle, and let's say we let x2 star just be this endpoint. Right? You can take anything in the subinterval, including the endpoints. In fact, in a minute, we will look at left and right hand approximations. So again, it's the width of the second subinterval, so that's delta x2, and then we want to multiply by the height, f of x2 star, which is the same thing as f of x2, blah, blah, blah. We did that for the general ith rectangle, blah, blah, blah. Do it for the last one. So now you've got n rectangles. We will find the area of these n rectangles and add them all up. That's going to be the approximation to this area using n rectangles. So the approximate area using n rectangles is given by this thing. Again, we want to use a summation notation. We'll look at that in the next slide. And so how do you find the exact answer to this area problem? Well, you let the number of rectangles go to infinity, right? You make these rectangles thinner and thinner, right? That will give you more and more rectangles, right? That will let the number of rectangles go to infinity, and the approximation gets better and better. In fact, it approaches the actual area. Okay.